You know the scenario. Um, you're watching a user click place order in the UI, and under the hood, your API is instantly trying to do like 7 different things at once. It's writing a database row, it's charging a credit card, updating the inventory ledger.
And emitting an analytics event, sending the confirmation email, notifying downstream fulfillment systems, and, probably kicking off a machine learning fraud check, too.
Exactly. And suddenly, that user's latency is just being held hostage by your absolute slowest dependency.
Oh, for sure. It's a classic trap.
Right. Like when one sluggish third-party email provider starts taking 3 seconds to respond, your entire product feels completely broken to the user.
Right.
I mean, that is the exact moment a queue stops sounding like mere infrastructure plumbing and starts sounding like, well, your core architecture.
Yeah, it's the realization that a queue is not just this magical mechanism to do work later. It's an active architectural boundary. You are making a really hard decision about which work simply does not belong in the synchronous request path at all, and deciding which work absolutely must be completed before you return that 200 OK to the client. Absolutely. But today, we're building a crisp mental model for when work should actually leave that request path. Like what delivery guarantees really cost you in production and how your specific technology choice shifts the burden of replay ordering and failure recovery.
Let's just unpack the core concept here first. The whole foundation of event-driven architecture is decoupling the rate of creation from the rate of completion. And the physical analogy I always come back to is the loading dock behind a massive retail store.
I love that analogy. It works perfectly because it isolates the environments completely.
Right. Customers interact with the front counter, that is your synchronous request path.
Yeah.
They expect a fast, clean transaction.
Yeah.
But the heavy pallets, the restocking work, the inventory reconciliation, all of that happens behind the scenes on the loading dock.
Yeah.
You separate those concerns specifically so the checkout line doesn't get blocked by, warehouse operations. And this brings us to the fundamental fork in the road for message routing. Point-to-point versus publish-subscribe or, pub-sub.
That distinction dictates your entire system's topology, really.
To stick with real-world analogies, point-to-point feels like assigning one specific repair ticket to one specific technician. It's a very targeted assignment. But pub-sub is like posting a building-wide incident notice. Security, facilities, IT, they all read the exact same notice on the wall, but they react completely independently. Right. Okay, let's move down the pipeline. We've routed the message correctly. We send our command or our event out into the broker. What is the broker's actual promise that the payload will get to where it needs to go? Because we talk constantly about delivery guarantees, but the reality is often way messier than the documentation suggests.
The practical default across almost all distributed systems is at least once delivery. The broker basically promises that if it's not absolutely certain the consumer successfully processed the message, it will just deliver it again.
It's like sending a piece of certified mail with an incredibly aggressive mail carrier. They will keep attempting delivery over and over until you explicitly sign for it.
That's a great way to put it.
Because in a distributed system, it is far better to risk another annoying knock on the door than to quietly lose the package in transit.
Yeah, that prioritization of durability over elegance is what keeps systems reliable. But the tax you pay for at least once delivery is that your consumers must be idempotent.
And as anyone who builds these systems knows, idempotency is rarely just a clean toggle switch in your code. It is incredibly difficult to maintain across distributed boundaries.
Very sure.
I mean, if my consumer reads a message, calls the Stripe API to charge a user $50, and then the worker node runs out of memory and crashes before it can acknowledge the message back to the broker, that message is coming back. The broker doesn't know about Stripe. It just knows it didn't get an acknowledgement.
Which is exactly why duplicate handling is not some nice-to-have extra feature you build during a hackathon. It is baseline correctness. Your consumer needs a way to look at that second delivery and say, wait, I have already processed this transaction.
Right.
And then return a successful acknowledgement without hitting Stripe again. You usually solve this with an idempotency key, so some unique identifier tied to the original request that the external API can recognize, or a deduplication table in your own database.
I constantly see engineers try to avoid this architectural tax entirely. They always ask, well, why not just go into the broker settings and turn on exactly once delivery?
Oh, please do not do that. Because exactly, once delivery is a severe cross-system coordination problem. It's not a magical infrastructure setting. Precisely. If you assume the broker is handling exactly once for you, you are going to double charge your users. You have to design for duplicates.
Okay, so Since we can't guarantee exactly once without massive coordination overhead, let's talk about ordering. I feel like there's a very naive assumption engineers make early in their careers, like, I produce these messages in order ABC, so the consumer will naturally process them in order ABC.
Yeah, the physics of distributed systems dictate that total ordering, meaning every single message across the entire high-throughput system stays in a perfect, absolute sequence. It creates a massive coordination bottleneck.
What all nightmare.
If you want strict total ordering, you can really only have one single partition and one single consumer.
You're forcing your entire global architecture to stand in one single file line. It defeats the entire purpose of distributed parallel processing.
On the other end of the spectrum, you have no ordering, which is highly scalable. You just have a pool of workers grabbing whatever is available. But that obviously breaks business logic.
Right, because you cannot process an order-fulfilled event before the order-created event. You'll hit foreign key constraints or just put the system into a completely invalid state.
Exactly. So the industry standard middle ground is partition ordering.
Okay, break that down for us.
You take a routing key, like a specific user ID or order ID, and you hash it. That hash maps to a specific partition in your broker. By doing this, you ensure all messages related to that specific order go to the same partition. And within that partition, they stay strictly ordered.
So Order 123's created, paid, and fulfilled events all land on Partition 3 in the exact sequence they occurred. And one consumer reads Partition 3, so that order is processed perfectly sequentially.
But meanwhile, Order 124 is hashed to Partition 7, and Order 125 is hashed to Partition 2. Those are being processed entirely in parallel by different workers.
Oh, it's brilliant.
Yeah, you preserve the sequence that actually matters to the business logic without creating a global bottleneck. They really do. In a traditional queue, state is managed by the broker. A message is handed to a consumer, the consumer acknowledges it, and the broker effectively deletes the message from the queue.
It's like a physical to-do slip pinned to a board. You pull it off the board, you do the task, you throw the slip in the trash, it's just gone forever.
But Kafka's append-only log model operates entirely differently. Messages stay in the log. The broker does not delete them when they are consumed. It only deletes them when they hit a configured retention period, like, say, 7 days.
Right.
State management is pushed to the consumer. The consumer groups just track their own position, their offset in that log.
So if the traditional queue is a disposable to-do slip, Kafka is more like a security camera recording. The tape is running continuously. The security team can watch it live at the front of the log, but the facilities team can also come in tomorrow, set their offset back by 24 hours, and review exactly what happened yesterday.
That's spot on. And neither model is universally superior. It depends entirely on your use case.
So, regardless of whether we are using a traditional to-do slip broker or a security camera log, what happens when the system is hit with a massive, unexpected spike in traffic? I'm talking about Black Friday levels of load.
This is a crucial reality check. Queues do not buy you infinite elasticity. They do not magically solve the physics of overload. They simply store that overload temporarily as backpressure.
I picture backpressure like a highway merge lane during rush hour. The cars, the requests, they still exist. They haven't vanished.
Yep.
The system is just storing that delay in a highly visible, incredibly frustrating line of traffic. So what happens when a message just keeps failing? It hits the visibility timeout, gets requeued, a worker picks it up, shits a null pointer exception, crashes, hits the timeout again. Eventually, a well-configured queue will route that message to the DL queue, the dead letter queue. I've seen junior engineers look at a dashboard, see that failing messages were successfully routed to the DL queue, and just assume the error was handled.
ADL queue is quarantine. It is not success. Moving a message to the dead letter queue just stops the bleeding so a malformed poison pill message doesn't infinitely loop and block healthy traffic.
Right.
But if messages go to the DL queue and nobody investigates them, you haven't solved the underlying bug. You have merely built a much tidier form of silent failure. Yeah.
A queue is a boundary. It forces you to explicitly model the gap between a request being accepted and a request being completed.
Accepted merely means the front counter safely wrote the intent to the queue. Completed means the user visible outcome actually occurred on the loading dock.
Right.
Those are profoundly different system states. Queues force your team to make those states explicit, which is incredibly healthy for system design, provided you actually do the modeling, instead of pretending that accepted and completed are interchangeable.
This has been a massive shift in perspective on what it means to build async systems. For Chapter 5, we are going to stay right here in the world of protecting the request path, but from a totally different angle. We'll be looking at how to design a rate limiter to enforce fairness and survive malicious abuse. See you in Chapter 5.